All right, mechanics, new problem specifically constructed for the 2020 review period. Let's take a look at this. We have a launch tube of length L on a table, fires a projectile that has an exit velocity of V. It started at rest, has mass M, and then that guy is going to collide and stick into a block of mass M and then slide across the table, coming to stop in distance D. This is the exact kind of problem, with a minor change of focusing on the tube as well, that we discussed in class. So the tube is going to do work on the bullet, and then the bullet is going to collide in an inelastic collision with a block. And then friction is going to do work and bring that whole system to rest. All right, so let's see here. Students experiment with a variety of tubes, assuming that the air resistance is negligible and everything else remains the same. Let's talk about the length of the tube, because we want to make the stopping distance the longest. So let's make up our own kind of situation here, where we're going to talk about force, because they want all other parts to remain the same, and they tell us that it's going to have a constant force. So force and distance together should indicate that work being the integral of f dot dx, and they tell us that f is constant for part A. So we can bring that out of the integral and just integrate distance. We're going to go from 0 to the length of the tube. So the work being done is F times L. Work is also going to change the kinetic energy of the bullet, so that we have 1/2 mvf squared minus 1/2 mv naught squared. And in this case, we want the bullet to be starting from rest, so that part's 0. And this Vf is the launch velocity V. So we'll just rewrite that with the terminology that they gave us, V squared. All right, and then it's going to fly a very short distance and collide inelastically with this block. So then we have collision with block. So we're going to have momentum initial equals momentum final, and we will have the bullet, mv, is going to cause the block and the bullet together to slide, and with speed v. And then what's going to happen is we're going to have work done by friction cause the bullet and block system to slow down and stop. So then we're going to have minus force of friction times distance, and I'm going to use a different symbol here, S, instead of L or D, because L and D show up later on. And we have 1/2 mvf squared minus 1/2 mv naught squared. Now in this case, when we're talking about the collision, we come over here and we say that these guys slide a particular distance, then they come down here, and we have the bullet inside the block like that. And let's see here, do they give us in this part? Oh yes, they actually do give us the distance d. So what this means is down here I can use distance d when we get there. And they will come to rest, so that's 0. And this v here is this v prime up here. So v prime is equal to mv over m plus m. And force of friction is going to be mu times weight. So substituting all of these guys together, we're going to have minus mu m plus mg, and they told us that the distance that I called s is actually d, and then minus 1/2, and this m is the mass of everything, so we will have m plus m, and that velocity is this guy up here, mv over m plus m. Don't forget to square it. Oh yes, and you also have to keep in mind that this velocity is the result of the work being done up here. So the work being done up here says those two guys should be equal. FL equals 1/2 mv squared. So we can, we've got an m and a v squared up there. We've got an m and a v squared down here. So let's just say v squared is equal to 2FL over m. Let's see if we can clean up this mess down here a little bit and look at relationships. So those two masses disappear, and the minus sign disappear, and we're going to have mu GD equals 1/2 m squared over m plus m, and then that v squared is going to turn into 2FL over m. So we have 2FL over m. And we can cancel out a couple more things. So that 1/2 and that 2 cancel, and that m cancel, and I have a feeling that I've dropped a square. Yes, this m plus m here should be squared. So we're going to have mu GD equals m over m plus m quantity squared times FL. And you know what? We can stick m, f, l all on top of the equation there. So what did we just string along together here? Well, we said work is force times length. So the longer the length, the more the work done. The more the work done, the more the kinetic energy of the bullet when it comes out of that tube. The more the kinetic energy of the bullet, the more the momentum of the bullet in the collision. So the bigger the V over here means the bigger the V prime over here. Okay, now the bigger the V prime over there means you come down here, and when we have friction doing work on the bullet and block system together, it's starting out with a bigger velocity, which means that, well, it's this distance that is going to get bigger because we're not changing the weight of the blocks, we're changing the velocity of the blocks. So changing the V is also going to change the distance d. So to bring it all the way back to the beginning, if we make L longer at the beginning, makes V bigger, makes V bigger, makes D longer at the end. Okay? And we need to string these guys along together by saying 1 longer, more work done. 2, more work done. Oh, down. Where did that come from? Done. More work done. More KE. 3, more KE. More original momentum. More original momentum. More final momentum after they collide. And then 5, more final momentum. That's an arrow. Let's see here. More distance needed to stop by friction. All right, taking a look at the answer key, you get points for saying longer, more work done. You get more points for saying more work done means more kinetic energy. And actually these two guys go together. And more kinetic energy means more momentum. Then you get another point for saying more momentum at the beginning gives us more momentum at the end for the collision. And then you get a fourth point. I split up 2 and 3. They combine 2 and 3. So the fourth point is for saying now that we've had more velocity because more momentum, we're going to need a greater distance on the end. And I wrote out all of the work here from beginning to end for this problem so that you see how it works. Now I'm going to have to clear it out so that we can take a look at part B. All right, for part B, they give us an equation, which if you take a look at my equation that I've moved up here to the top that I ended up with at the end of part A, I could finish solving for the distance by moving the mu and the g, and I get exactly the same equation that they got. They gave us the equation, at least the final equation, indicating the relationship between the sliding distance d and the original length of the tube L. So this, if you take a look at this, the functional relationship is L is in the numerator, so if we increase L, we're going to increase D. And that's all they want you to say is, looking at this equation, yes, that fits with what I said. A longer length tube will result in a longer sliding distance, D, because L is on the numerator of the fraction, so increasing L will increase D as they are proportional to each other. All right, part C. Now they're going to change things on us. Classic AP style question. Now they're going to say the force is a number times distance. Notice that force depends on distance. It does not depend on time, at least not directly. So what they're getting at, what they want to see is force is the integral of distance, and because we're going to have a 2 meter length tube, we need to integrate from 0 to 2, and then set that equal to kinetic energy. And what you will see when you do that is that the work is proportional to distance squared, which is also proportional to velocity squared over here. So what you need to explain that you're going to do is you could use the equation by integrating with respect to distance, setting it equal to velocity, setting it equal to not velocity, but set it equal to kinetic energy, and then you solve for kinetic energy, solve for velocity by dividing both sides by mass, canceling out the 1/2 and taking the square root. And what you end up seeing is that velocity is directly proportional to length again. All right, part D. Predict what will happen to the launch velocity if the length of the tube is doubled. Okay, so if we double the length of the tube, oh, wait a second, I forgot to write the squared there. All right, so if we double the length of the tube, we're going to square that, but then we're going to square root it. So V is equal to x square root 12 over m. So for part D, double the length of the tube will double the velocity, because once again, the length is in the numerator. What we need to have is the mathematical functional relationships between the distance and the velocity. All right, so double length, double velocity, because length in numerator. All right, part E. Students are given the equation for the velocity, which I've derived here for you, and you would do this on paper, as follows. Without algebraic, okay, does it match your explanation in part D? Yes, it does, because once again, if we double the length, we're going to double the velocity because the length is in the numerator. And that's all they want to say, all they want to see from you is that you understand that this relationship here accurately describes what they were hoping you came up with before. Now, you're going to be typing in all of these explanations, but it will help you to have a piece of paper to work through the calculus and the algebra. And the big things that you need to remember are when force is a function of distance, then what they want to see is work is the space integral of force. If, however, they give you force as a function of time, then they want to see is impulse is the integral of time.